My name is Jana Kolar, and I'm the current chair of ESFRI. Now, the objective of these open sessions, which were introduced 2 years ago, is to inform, showcase the work of research infrastructures in the different domains to ESFRI, but also to broader audience. Now, exchange of information between ESFRI, European Commission, and research infrastructure is strengthened in this way. And this exchange also allows to learn for ESFRI members and European Commission to learn about the activities of research infrastructures and learn from you, so we can do our work better. So we are very happy that now we are in the third organization of this open session. And as opposed to the previous time, it is also open to a broader audience. Now, the agenda, when setting up these open sessions, we have discussed that agenda should consist always of 3 different points. The first is the report of the ESFRI chair, which I'm doing now. The second one is presentation of the ESFRI projects or landmarks, representing a particular strategic working group. And the third one is supposed to be presentation of the European Commission activities related to research infrastructures or research infrastructure landscape in one of the ESFRI member states or the stakeholder organizations. Now, it was decided that for the first 3 rounds, and this is the third one, this last point is not included. Instead, we have a presentation of another strategic working group, research infrastructures. So, as with the last, the past 2 open sessions, we will have first the presentation of the chair, and then 2 strategic working groups. In this case, physical sciences and engineering, and digit. In the first session, open session, it was health and food and social and cultural innovation, and in the second one, environment and energy. So let me now briefly review the activities of ESFRI for the next 2 years, because we have just during this ESFRI meeting discussed the draft work plan for the next 2 years. Actually, now it's only 1.5 years. And it's a very ambitious plan. Now, first of all, you have heard probably in other fora that we have a new governance and implementation of European research area. And it's implemented through 3-year activity organized in ERA actions, and ERA action 8 out of 20 is dedicated to research infrastructure. And there's a number of activities which I will briefly review, based on which you were also invited to numerous meetings over the past few months. And then we have also added, in addition to ERA action 8, additional activities at ESFRI. And I will briefly go through these topics in order to then leave the space for the presentation of research infrastructures, which we are eagerly awaiting. So first of all, I'll start with Action 8. What we plan to do is the strategic analysis of European research infrastructure landscape. To this end, we kicked off this activity with a workshop. It was an exploratory workshop. What is good, what is bad, how we can improve in the future, what should be the objectives and the results, and so on. So the objective of this activity, the landscape analysis, which is called strategic landscape analysis, as opposed to the one that was published in December as a part of the roadmap. Now, strategic, because it will take a longer time, go more deeply into the topic and be decoupled from the roadmap itself. So as it should, basically, it should feed into the preparation of the roadmap. And what we hope to achieve with it is to identify trends and gaps, also facilitate better coordination between research infrastructure and integration, so that we would not be establishing new infrastructure where coordination or integration could fill the gap. Prioritization of landscape will be very relevant also for the road mapping process. But also with the process, we want to highlight the role of research infrastructure to various communities so that they would be used even better than before, and possibly also to increase their user communities. Now, another activity is monitoring of research infrastructure. You've probably heard about this one, at least research infrastructures on landmarks on ESFRI roadmap, because we have decided that they need to be, that these infrastructures need to be monitored. Now, at European level, from ESFRI, they receive a landmark status. And of course, it's not forever. It needs to be quality checked. And for this reason, we are putting in place monitoring framework in order to monitor all of the landmarks within the next few years. Now, we have had one workshop already to discuss with research infrastructures how this should be done, and we'll have another one in September, hopefully in September, in order to discuss with research infrastructure the process and the exact implementation that will be prepared by then. Then another activity is update of the ESFRI roadmap methodology, which I mentioned will be based on also on the outcomes of the landscaping activity. Additional activity that we will engage with is broader and more sustainable access for all countries to European research infrastructures and their services. And next to this, revision of European Charter of access to research infrastructures. These two will be dealt with by one task group, that task force, which will look in detail at the how to implement these two activities, and we will involve the stakeholders again in this, as we cannot really come up with a good proposal without you. Obviously, you are the one that used the charter most, for example, just as an example. The second to the last activity on the link to the ERA Action 8 is report on the ERIC framework. This one is being prepared by European Commission. What we have done already at ESFRI is to provide input, and we looked in particular at how to involve also RIs beyond the ones on the ESFRI roadmap in the activities of ESFRI. The last one is the stakeholder engagement strategy. This is the activity of carried out within ESFRI, where we are looking at how best to engage with the broad communities of stakeholders. And hopefully we will have this set up by the next meeting in October. Now, in addition to this ERA Actions 8, which are a part of so-called ERA policy agenda, implementation of the 3-year cycle of the ERA policy implementation, are specific activities which at ESFRI we are discussing in order to either help member states or research infrastructure, for example, with the sustainability. The topics here are, for example, meta-analysis of impacts of research infrastructures, because it's extremely important that research infrastructures are able to do high-quality impact assessments, and they can learn from the past impact assessments that are undertaken by other research infrastructures. But also it's important for us to be able to communicate to various communities your impacts, especially to the funders, because it's, you know, ESFRI, it's 24 billion investment agenda, and we need to demonstrate the value that comes out of it and the excellent science that comes out of it. So in addition to this activity on the meta-analysis of research infrastructures, there was a questionnaire circulated among research infrastructures on to what extent they cooperate with industry. And this is extremely important in view of future developments, also with respect to, for example, technology infrastructures. We basically need to know your activities, your engagement with and services to the industry better. Another questionnaire, which have been sent already to the, in this case, to the ESFRI delegates, is on the research infrastructure funding, where we want to learn how research infrastructures are supported in various countries, from which funds are they supported with short-term or long-term measures, and similar. International cooperation is another activity. Now, during the Czech presidency, there will be a declaration, Brno declaration, linked as an output of the ESFRI International Conference dedicated to the global view. Now, in our case, what we would like to do is to look at it from the European view. Additional activity is increased transparency of ESFRI and ESFRI support structure so that we could function better. Now, several events in the near future will be organized to support the development and delivery of this ambitious plan. So I kindly ask you, please stay tuned, and we'll be looking for your inputs in order to develop this agenda further. Thank you. So with this, I conclude my brief introduction and overview of ESFRI activities, and I pass the floor to Christian Temst and then Anna Projkova, who will briefly introduce their respective speakers and also then moderate the discussion. Christian.
Okay, thank you, Jana. Thanks for the introduction. And good afternoon to everybody. We're really delighted that so many people have decided to join this session. I'm the chair of the Physical Sciences and Engineering Strategic Work Group. And for today, we are very lucky to have three distinguished speakers, Gonzalo Merino, Jean Dayan, and Rosie Bolton. And if you look at the research infrastructures with which they are engaged, then you see that the science that is done in these infrastructures covers an enormous gamma of spectrum of length scales, going from subatomic particle physics all the way to entire galaxies. And so we're very eager to learn from all three of them what are the specific challenges regarding data that they encounter in their work. So we will have the three lectures coming right after another. If you have any questions, please put them in the chat. And then after the talk by Rosie, I will moderate the questions with our three speakers. So I hope that you will enjoy this session devoted to physical sciences and engineering. And without much further ado, I would like to give the floor to Gonzalo Merino. Gonzalo is director at the Port d'Informació Científica in Barcelona. So Gonzalo, please go ahead. We see your slides, but we don't hear you right now.
Okay, yeah.
Okay.
I was muted. Sorry about that. So, okay, slide sharing is working fine, right?
Yes, perfect.
Okay, thank you very much. Sorry for that. Well, first of all, thank you very much for inviting me to give this talk. I'm Gonzalo Merino from the PIC data center in Barcelona. And I'll give a short overview, of what I see as the challenges in our field. So let me see, first slide. So just wanted to start with this small sketch where maybe just to state the obvious, but I think I always like to point this out. So I try to convey the idea that in experimental science today, digital infrastructure is an integral part of instrumentation, right? So a part of the experiment equally needed as the sensors, cameras, microscopes, or detectors we are used to. So I like to think of computing as another sub-detector. Sometimes that's useful also to convey this idea. So it's equally important as any other sub-detector, and mainly because without it, there are no scientific results. So as an example of some of the challenges ahead in our field related to data analysis, I'm showing here the projected CPU needs of ATLAS, which is one of the 4 experiments in the Large Hadron Collider, for the next decade and beyond. So we see the rapid growth of computing needs, especially around 2028, when a new data taking period will start with an upgraded accelerator, upgraded detectors, that will result in this 10 times more data and more complexity expected. So in this graph, we will not enter into details, but there are the blue and red lines depict the different scenarios. With the blue would be more conservative, the red more aggressive. The main difference is the amount of manpower you can dedicate to do R&D to actually improve your technology. The black lines show the evolution corresponding to a 10% or 20% yearly improvement, yielding annual capacity increases. So which is the current assumption for what might be achieved in a flat funding scenario. So first of all, these projections are regularly updated by the experiments because there is a constantly R&D activities are going on. So the good news is that as we are looking at these projections year after year, the situation is improving. The gap is getting smaller and smaller. So 3 main messages I wanted to convey from this kind of picture. So first of all, that it's very important. It's necessary to increase the person power to do R&D, because that's the ingredient that brings actually those graphs down and allows us to do more, to handle more data with new technology. Second message is about these projections of flat funding scenarios, sometimes we call them. So pointing out that 20% yearly capacity increase is definitely not guaranteed. We've seen in the last months, in the last year, heavy local fluctuation, right, in terms of costs. So this is a sizable risk we need to be aware of. Third message is that we also need to think about the operative costs. So for digital infrastructures in particular. So those are also rapidly increasing. So we are thinking about, for instance, electricity costs that used to be below the 10% in a facility today are more into the 20s and 30% and rapidly growing. So things like energy efficiency are definitely moving quickly very high into the priority list. So I wanted to point out this idea that computing, it's in a turning point, right? So for decades, the Moore's law and their scaling enabled these exponential performance gains. So we were used to this constant improvement. And this has now changed. This has changed since several years now. And all the improvements come at the expense of increased complexity. So all the semiconductor advances are getting more and more expensive. The consequence of that is more complexity. So basically along 2 axes, on is more parallelization, to making use of these multi-core architectures, also GPUs. And on the other hand, also distributed computing. So making use of any resources out there, wherever they are. Again, this is increased complexity, and the challenge there is automation and orchestrations of complex distributed services. So an important component of this distributed landscape is the HPCs, high performance computing centers. So these systems are in the strategic agendas of many countries and in Europe as a whole. So we are expecting petascale, exascale systems are in the roadmap. And of course, scientific experiments will have to make use of them for their data analysis. So this is not easy, and as these machines are very, very specialized and are quite different of what sometimes our scientists are used to. So it's important to remember to point out that there are barriers for the adoption of this idea. Access policies in these centers are different. Wide area networks and these machines are not really designed for massive input and output, or even sometimes processing nodes have no outgoing connectivity. So anyway, technical barriers that will need to be addressed, and it's important to make sure that we put the effort in there. Also, HPC landscape is very much heterogeneous. Each machine is, for good reasons, different from the other one. There is a lot of GPUs in these machines, so the success in exploiting GPUs will play an important role. Another important component of this distributed landscape will be the cloud. So just to recall, and we all know that the main advantage of the cloud is its elasticity, right? So there is this huge advantage for companies, for instance, with variable IT loads that are depending on demand, and this has had a huge economic impact. But then not all of the companies have variable loads, and not all of the loads in a company or in any other place are variable. So companies that have predictable loads have gone back to on-premise in recent years. And we need to remember that a big portion of scientific computing is actually predictable in terms of data processing. So cost of data handling is still high in the cloud, but of course this is going to change tomorrow. So this is the main message is that this is a very continuously evolving environment. And it needs to be tracked. So there are important large-scale initiatives out there in scientific collaborations, actually testing this at scale and monitoring this at scale to understand the TCO involved, etc. Wanted to point out quickly to a couple of important initiatives, I think, in Europe. One is OCRE, which is an EU-funded project that has established a framework of agreements with cloud providers to facilitate the administrative processes at the institutions. Also Archiver, just two examples. So Archiver is an initiative to make competitive procurement of R&D for developing data preservation and archive services in the cloud. So finally, the final key message, I think, is collaboration. So the research environment, I think we'll agree that it's collaborative by nature, right? So there are two ways in my thinking that this is very important for digital infrastructures. So one is that the collaboration between different experiments and scientific disciplines, so this interdisciplinary collaboration. So lots of science programs are very long, spanning decades. So the sustainability is as big of a challenge than the performance or the capacity. So increased collaboration is, I think, one of the keys for this sustainability. Second point is that many of the large computing facilities support multiple experiments. So in order to scale and to meet the challenges, I think it's very important to realize that to enable more efficient operations through economies of scale and technology sharing between different experiments, between different fields. Along these lines, I wanted to finalize by pointing out to a specific example to exemplify this importance of collaboration. So I wanted to point out to this Horizon 2020 project that have been tackling this precise issue of collaboration in the last 3 years. So one of them is ESCAPE, which is a project where the ESFRIs related to astronomy and particle physics have been collaborating to develop a common EU infrastructure and have demonstrated advanced functionality on this shared technology. The ESCAPE project is actually 1 out of 5 projects that were funded in a specific H2020 call, aiming to foster this collaboration between ESFRIs to develop the EST vision. So the other projects group infrastructures, ESFRIs in environmental sciences or photon and nuclear sources, social sciences and life sciences as well. And I think it's worth mentioning that all of these 5 projects across all these diverse fields have been collaborating in these years among them. And I'm pointing here to a couple of position papers that have been written by this global collaboration during these years, describing their shared view on the role of research infrastructures in building this European open science cloud vision. So I just wanted to finalize with a summary and highlighting the main ideas, a few main ideas. So I think one of the main takeaways to me is that if we look at computing, this is currently an extraordinarily dynamic environment. So there are massive investments from industry, lots of innovation, and also what's also important, a fierce competition for talent. We feel that every day. So the environment is is defined by short cycles. So agility and being able to implement iterative improvements will be a key. So we need a framework to process and manage this change somehow. Along these lines, it will be very important to engage with industry, of course, to co-develop and integrate all these new technologies that are all the time appearing. So one of our biggest values in the research field is our unique data. So we need to prioritize continue generating this high quality data and preserving it for the future. So this is challenging because we are talking about multi-decade timescale experiments. So it's important to realize that we need to think of organizations with sustainable funding models, technical expertise in data management, trusted, etc. So this is important to keep in mind. So also, the third point is that computing, I think, must be considered not just part of the running or operational cost of experiments, but actually an integral part of the design and the construction, and as well of the costs. So this means, for instance, that we need to put in place or make sure that we have incentive schemas for institutions that contribute to computing to be acknowledged, similarly to what happens with the detector constructions, for instance. And also things like a recognized career path for research software engineers. That's also very important for the sustainability. And as a final point, I wanted to come back to one of the main themes, I think, of my talk, and underline the importance of collaboration to tackle these challenges. So I think we will need to build federated e-infrastructures supporting multiple disciplines. So then creating the needed structures and governance for this collaboration to happen and to thrive, I think it's one of the keys for success. And that's what I wanted to tell you today.
Thank you very much, Gonzalo, for this interesting overview. We will now continue immediately with the next speaker, which is Jean Dayan. Jean is the Director General of the Soleil Synchrotron, and he is currently also the Vice Chair of LEAPS, which is the League of European Accelerator-based Photon Sources. So Jean, the floor is yours.
Now it should be okay.
Yes.
Yeah, fine. And you see my screen?
Yes, perfect.
Very good. So thanks a lot for the invitation and introduction. So as you said, LEAPS is in fact a consortium gathering all synchrotrons and free electron lasers in Europe. We think it is the largest consortium of analytical facilities worldwide, with something like 35,000 users. And we are in LEAPS 19 facilities from 16 institutions. Regarding data, we have also a long tradition of working with the neutron sources. And this started with several European projects more than 10 years ago. I mean, starting with common data policy, also having a single portal for access to the different facilities, and so on. And so this is really where we are. But of course, I mean, we see a very large increase in data production, which results in issues like data storage, transfer, processing, but also opportunities like the use of artificial intelligence. And maybe I should say that when we say data, we basically have two types of data. Of course, we have the data of our users, but we have the data we are generating ourselves with the operation of the facilities, and where, in fact, I mean, big data techniques can also bring a lot of improvement. Of course, we are in, I mean, applying FAIR principles, and we are also looking for integration in the EOSC. All this implies offering remote services, requiring appropriate infrastructures, which was just the subject of the previous talk. And regarding this, I think the trend is really to use national or research organization-based infrastructures, but in any case, bigger than what we can do at our synchrotrons or free electron lasers. And we would like to have an implementation as close as possible to the data source. And of course, I mean, as was just said before, human and computing resources are an issue. And here I would also like to mention that 8 of the LEAPS affiliated facilities, which means half of them are already members of the EOSC association. From our users, we have, I mean, clear request, which is to have good metadata, which can be, I mean, automatically collected or not, and logbooks, performant download services, DOIs for data, remote data analysis services, access to open data, credit for data reuse, and of course, help in data management. So, I mean, all together, looking at not only synchrotrons, free electron lasers, but also our friends from the neutron facilities, we are involved in 2 important H2020 projects, which are PANOSC, which has already been mentioned in a previous talk, and gathers ESFRI infrastructures and ERICS, and EXPANSE, which is complementary to it, but for national infrastructures. And we are closely working together within the 2 projects. So on the slide, you also have some, I mean, predictions for the, I mean, data production rate. If, I mean, I go a little bit more in details into the goals of the 2 projects. So PANOSC will have a focus on data policy, data catalog services, analysis services, virtual neutron and X-ray laboratories, which means, for example, possibility to simulate experiments in digital twins, EOSC integration, sustainability, staff and user training, and of course, outreach, communication, and so on. And for EXPANSE, the specific goals are data management, sustainability, enabling fair data for national facilities, again, data catalog, data analysis, and training activities. And I mean, what I should say is that, I mean, here we have something like 20 partners with different constraints, different goals, which means that we will for sure not adopt a single solution for each of the goals we have, but there is obviously some diversity, for example, in data catalogs and so on. So, I mean, interoperability is definitely something which is very important. Regarding LEAPS itself, we are working in a different project where the focus is on data reduction and compression. And here, what I just want to illustrate is that depending on the techniques, the needs for data compression can be quite different. It can be speed, it can be ratio, it can be decompression, and so on. And so we also have to, in fact, take into account all this complexity. So some highlights from the two projects. And it's clear that we have not achieved all this yet, but we are actively working to complete this list of goals. Fair data policy and DMPs is quite advanced. We also are working on a common framework for generating identifiers, standardized metadata, which involves both a data format, and there I think there is an agreement that we will work with Nexus HDF5, but something which is a huge work is also to work on ontologies, and there is a photon and neutron ontology which is being completed. But of course, this is not enough for the metadata, as our infrastructures are very multidisciplinary. Search APIs for data catalogs, open data portal for searching and downloading data, all the authentication issues, Jupyter notebooks. Visa is a platform for data analysis, which has been developed at the ILL, the neutron source, but which we are going to implement as a standard. Software for the simulation of experimental data, and of course a training platform. And just to show you where we are for regarding the different facilities and the different subjects. So you see that maybe 20% of this is already functional. A lot of items are in progress of being adopted, and some under evaluation, and some will not be adopted by some facilities. And with that, I thank you for your attention, and we'll be happy to answer questions at the end of the session.
Thank you very much, Jean, for this very interesting overview and the approach that is being taken in leaps and lengths. And then we come to the last speaker for the PSE part, and that will be Rosie Bolton. Rosie, the head of data operations at the Square Kilometer Array Observatory. So Rosie, the floor is yours.
Okay, great. Do you hear me all right?
Yes, perfect.
Yeah, good. Okay, brilliant. So yes, I will. I'll kick off. So yeah, I am the head of data operations at SKAO, and I guess it's, yeah, we're in an interesting position because we don't yet have a facility, but we are now constructing it. So we're looking towards the challenges of big data and allowing it to shape how we design the observatory itself as we build it. So in case there is anyone here who is not aware of SKAO, the Square Kilometer Array Observatory's mission is to build and operate cutting-edge radio telescopes that will transform our understanding of the universe and deliver benefits to society through global collaboration and innovation. Again, this is another example of a multi-decade project. So the plan is that SKAO will start operating fully by 2029 and run for approximately 50 years. And as I said, construction is underway now. Telescope foundations are being laid at the sites that we have. So what does this mean we're building? So we have two interferometric array telescopes forming our observatory. One of them will be in Australia, that will be working in low radio frequencies. And that Australian telescope will consist of 131,000 individual antennas spread across the Western Australian desert. And then we have a second array, which we're building in South Africa, which will consist of 197 dishes, which operate at medium radio frequency. And they also will be spread across the South African desert as well. So we have very, very many antennas and very many component parts detecting signals, pulling together the images from the sky or data from the sky that we then turn into the needs of the users. So trying to frame this in the big data context, and I've chosen to go along the path of the classic 5 V's of big data. So one of those V's is velocity, and the way that SKA has had to respond to the velocity of data in its design is really around the rate at which it will collect the signals from the sky and thereafter have to process them through different parts of the system to condense them down. So this is a way that, within the observatory, we need to move from the general ability to detect quite broad areas of the sky down to the specific needs of the users to deliver science products that will enable them to do their specific science experiment. So as we move through the stages in the system, we move from generality to specificity, which might be, a very well-defined output data type, looking at a particular galaxy in a particular frequency range with particular parameters used in the processing to get to it. And that all has to happen within the observatory because we have to handle this velocity. There's another way of thinking about that is, as Gonzalo said, that for SKA, very much so, the science data processors, the supercomputing facilities, which amount to 1/4 of an exaflop machines in combination, 2 of them, they are fundamentally part of the telescope. They have to be scheduled and planned alongside the planning of the observation of a particular part of the sky itself. So it's not just that we need a certain number of antennas available, we need to know that we have capacity within the SKA computing to do the processing to get to these data products. And thereafter, once those products are made, we need to pass them around the world so they can be accessed by the users. And so it's that point of delivery where we have data products and we then pass them on to the users that we move from the observatory domain into a global collaboration domain, which we call SKA regional centers. Let me just go to the next slide. Sorry, it's not wanting to do that. So the idea is that to handle this volume, so as we move from velocity, where we have this throughput issue, into a volume issue where we're not so worried about throughput, it's the overall size of the data products that we're worried about. We foresee having a global network of SKA regional centers spread around the world and working collaboratively to deliver access to the products to SKA users. And that is an interesting challenge. So as I mentioned in the previous slide, that the output data rate of SKA will be approximately 100 gigabits per second for each of the 2 computers delivering data products. That amounts to, when you add on user-defined data products, approximately an exabyte per year of long-term archive growth that we have to plan for. We're not quite sure what it will end up being because it depends on the science that gets done, but we need to plan for exabyte scale per year growth in the archive. Fundamentally, because those SKA computers are not, because they're part of the telescope itself, they are not accessible directly to the users. So users can only go to these regional centers to analyze their data products. They will not be able to get hold of raw SKA data. There's too much of it. So within the observatory, we will see something like a 40-fold reduction in the amount of data. And even at that reduction, we still get an exabyte per year coming out. So we are definitely in the big data volume. We also have to bear in mind that the users themselves, when they're doing their analyses, they could have data sets which are up to tens of petabytes in size for a data set that needs to be co-analyzed. And so we need to think about what that means for the structure of the regional centers, what it means for how they interact with each other, how they share data try and minimize the movement of data between sites, because it will be a bottleneck and very expensive. So we hope that we will use SKA regional centres to bridge the gap between the specific outputs that have been asked for from the SKA, and then the kind of user-led analysis that you would end up putting in a paper. You know, what do you need to do the science? We also have to cope with the variety, Livy, of big data. So the observatory data products will be predefined, but there are very many different types of them. And we have to accept that within this global collaboration, the users want to develop their own data products, and we can't pre-select what they're allowed to do. We need to allow flexibility. We need users to be able to bring their own workflows into whatever systems they're using. And we will offer an SKA science platform in these regional centres. And one way we hope to improve things is by having some standard templates so that compute efficiency can be improved when users are bringing in their own software. So there's work yet to be done. And another very important V of big data as far as SKA is concerned is the veracity of the data. So really this is about trust. You know, how much can we trust that when we're given a data product, we know what it is? And of course, the FAIR principles of findability, accessibility, interoperability, and reusability are really important for establishing the veracity of a data product. You know, can it be reused? Let's reuse it as much as possible. But you know, we also have to bear in mind how we will develop that. So keeping track of the provenance metadata would be one way forward. It's quite complex to do, but we'd like to capture for every data product that's within the SKA regional centres, what were the workflows that we used to develop it? You know, how has it come about? And can we trust that workflow? Was there a bug in that particular release of the software? Does it need to be rerun? And another way to build trust is through collaboration, which touches the same theme from what Gonzalo was mentioning as well. We need to build trust for users. So SKA will be a sort of paradigm shift in the way that astronomers will be accessing their data products. They won't be able to download the data products. They have to use facilities provided in these regional centres to interact with the data products until they are rendered down small enough that they could, you know, pop them into a paper. And that means trusting those sites, trusting that when they've run their workflows, it's done what it said, trusting that their data are secure in those sites and that they won't be shared, you know, outside of the teams that they're happy with. And one thing that we're doing to build up trust in those services right now is to start with a series of science data challenges. We've just had the second SKA Science Data Challenge, where teams from around the globe took part in a challenge to do some data analysis work on a simulated spectral cube of SKA data. And they were using facilities offered by a range of sites around the world as well. So 8 different supercomputing centres offered some resources into that work. And those was a step towards getting those users to understand that they can, you know, do their work remotely and trust the results that come out of it. And that's really important for the regional centres, because we need to move to a paradigm where the work is done on facilities which host the data, irrespective of the geography. So irrespective of where a user is from, they need to access the facilities close to the data where it's being stored. And the final V I will mention today is value. Again, this comes back to the reuse part of the FAIR principles as well. Data are only valuable if they can be used. And initially, SKA data will be developed with the needs of the specific scientists in mind who are proposing a project. But after a year or so, it will become public. And we need to make sure that it's as reusable as possible to get the maximum value down the line out of those data products. And that doesn't work unless you can play together with data coming out of other facilities. So we have to work alongside those facilities for ensuring interoperability. And one way to do that is through the International Virtual Observatory Alliance, use of those standards to ensure that we can cross-match different examples, different sources from different wavebands to see, what does this look like in the optical? How does that information influence how I interpret the radio map? So those are really important concepts. So all of those things together mean that we have a vision for SKA regional centres, which covers a whole range of different functionalities that have to be enabled. And we're now stepping down the road of building some of those software functionalities, as well as some growing hardware functionalities as well. So we've just started a collaboration to prototype these amongst our global teams, and that will be work that takes place over the next 5 years or so. So we're stepping down this process. So to summarize all of that, then, SKA as an observatory is fundamentally a big data machine, and for us, big data is not a research area or a kind of nice idea. It's not an academic concept. It's fundamentally part of the observatory. We wouldn't be able to build SKA at all unless we were ready for big data, because we couldn't reach exabyte per year scale. And that's really important. It's why we are in step with High-Lumi LHC in terms of data output as well. Now is the right time. This is the right decade to get ready for doing these very large data experiments, now that the world of big data is ready to support us in these goals. Okay, I'll stop there. Thank you.
Thank you so much for the interesting presentation. I would like to thank all three speakers for sharing their insights. We have a few minutes left for some questions and discussion. I see one question here in the chat. Are there effective protocols for accessing the same data sets by many users? Who wishes to respond to that question?
Well, maybe Jean, maybe Christian, if you wish, I can say a few words. That's
of
something
course.
which is really a very important issue, because at this stage for the LEAPS, of course, data are available to the experimental team from day one, and then after an embargo period will be open to the entire community. But we need to do something, which is to give access, for example, to members of a larger consortium than the experimental team. And we are working on that, but this is not something which is completely obvious. Okay, thank you. And maybe a quick question. Consumer electronics is hit these days by the scarcity of chips, computer chips. To what extent is that affecting your operations? Again, I could say that scarcity of human resources is much worse than electronic chips at present. All right. Okay, that's a message that is well taken. I see that there are other questions coming, but in view of the time, I would like to stop the discussion session here. I'm sure if there are more questions that you can address the speakers individually, but in view of the time, we should now switch to the second part of this session, and I take this occasion to warmly thank the three speakers for their excellent and interesting presentations. And I would like to hand over now for the digit part. Thank you very much.
Thank you very much for the floor. This is Anna Projkova, who is taking the floor to present the speakers in the sector of digit. This is quite an interesting new developing section where the digital infrastructure are coming to ESFRI landscape. I'm not going to talk long. And the very first speaker will be Professor Fosca Gianotti, who is a professor in computer science and coordinator of So Big Data, which is a new project that entered the roadmap in 2021, but actually it has been developing for a couple of years, and you will hear what Fosca will tell us about how this infrastructure responds to demand for cross-disciplinary research and innovation. Fosca, you have the floor.
Thanks. I will share the screen. And okay, see here. Okay. Okay, so can you see the screen? So thanks very much for inviting Big Data to this session. So big data means social mining and big data ecosystem, and the social mining is the very magic word. So the idea is to respond to the demand of cross-disciplinary data-driven research innovation from many scientific disciplines that want to observe society, both at the individual and collective level, through the lens of the digital breadcrumbs which are available so far. So there are data which are produced by our activities, the human activities, through the many devices, and they really offer an interesting new microscope to a different sorry. Okay, so a different to different researchers from different perspectives. So the idea was to. Sorry?
I succeeded.
Sorry, is there someone speaking?
Speaks now, please go on.
Can I go on?
Yes, please.
Okay. So it's so the idea was to provide a set of toolbox, social mining toolbox, to understand the modeling complex social phenomena and their evolution in time. So with this idea of not combining what is the repertoire of methods from data-driven, so machine learning, data mining, together with model-driven analytics coming from complex systems. So the idea also from the methodological point of view, also having different communities of, I'd say, modelers capable of providing methods. So there was the other important, let me see how to go down. Okay. So big data, we started with the initial steps were as an early stage research infrastructure with 2015, 2019. So we consolidated in the, and there were only 11 partners, but we started with this idea of creating very soon the infrastructure, the digital ecosystem, with starting with the point of view of interesting application societal challenges. You will see later on. So we started with 11 partners as initial starting community. Then in 2019, we applied for becoming a consolidated community, and we grow as in terms of partners. Now 31 partners and 13 countries. Then we applied for the ESFRI roadmaps, and new other interested partners and countries came with us. So Poland and Sweden also entered in the consortium. So the idea is that providing a rich catalog of analytical methods capable of working on different forms of data, image data, spatial-temporal data, text mining, text data, so a variety of different, so web data, different source of data, which are a sort of this mirror of human activities, and then a platform with computational resources, very similar to those we have already seen in the previous talk, and a big effort for having a distributed community of data engineering and data scientists, and all within ethical foundation. So since the 2015, we formulated a FAIR principle that was should have been, so imagining that working on data which are provided by human activities. So first of all, you need to guarantee privacy, you need to guarantee transparency, you need to guarantee accountability. So fair in terms of findability, so the properties that shareability, the goal of having open science should have, plus the properties that the kind of data that we are treating should also have, like privacy and what else. So ethical foundation for us was very important, so that the scientists that we have in this ecosystem are also moral philosophers, legal, not only digital with digital competences. So the kind of services that we provide so far, so there is the notion of exploratories that we will go later on, which is the way we include communities, multidisciplinary communities with their important scientific challenges, and with them we co-create the solution in terms of data-driven modeling and data-driven and maybe machine learning solutions. We provide validation, publish paper, but then there is this feedback loop that we will provide new data sets and new methods that enrich our catalog, capable of being reused even for a different purpose from different scientists. So we have sociologists, we have demographic, historian, but the data which are useful for an experiment might be reused again. So, and then, so we have the catalog, the lab where we can, the experiments, of course, with Python, all those technology, which was mentioned even before, it's available. And we have an e-learning area. We are also providing a variety of e-learning services, in particular for the libraries that we are using, with the idea that we can also disseminate the data science methodology also in other disciplines. So that's another important part. Of course, there is all there are other kind of services, ethical services. This is another important thing. So we have a board which is capable of helping the scientists to ask the right ethical questions since the beginning of a project. So all our projects in the exploratories are at this first meet with this ethical board that start helping them in making easy. I think that we have to disseminate this idea with the scientists that taking care of the ethics issues, it's something that is not a complex bureaucracy, but it's an added value to our science. And then, of course, there is a lot of initiative for community creations. So they have events, the transnational access, workshops, summer schools, and also we have a special program, Challenge Us, for innovators, where we challenge the startups, the company, to provide us some interesting problems, and we go with them to do the proof of concept. So the exploratories are those which are the multidisciplinary part, but it's fundamental for having new data, new methods. Now are 6, but it's an evolving. So the first that started since the 2015, we started with the exploratories. The idea was that we construct our catalog of methods, starting from the needs coming from the research questions that we can find in different disciplinary domains. So societal debates and misinformation, it is everything related to the information, which is the debates online, from fake news to bubble creation, what else? Bot detection, demographic economy, how to use big data for inventing, for providing new indicators that may be useful for even for official statistics, thanks to the fact that we have now these digital traces which can really help understanding new phenomena which are not miserable by the standard methods. Sustainable city of citizens is another enormous exploratories where data which are coming from mobile phone, cars, or even from Twitter are used for observing phenomena, mobility phenomena, and also environmental pollution in city. Migration studies, again, using Twitter for observing migration phenomena. And recently, the last 2 years, we have also a big attention for social impact of AI, both from ethical point of view and some both from the methodological point of view. So several other methods coming from several groups of the project working on explainable AI, on bias discovery, have been part of this. Okay, and that's sport data science and network medicine are two new ones. So that's just to give you the overview of the many disciplines which needs the integration of data scientist competences together with domain competence. They have nice modeling there that we need to provide a data-driven or model-driven approach. So it's we also have so that's so the fundamental goal was to work as a wind tunnel for this kind of very sensible experiments. So we have our provider RD4Science, of course, and all the services that we provide in So Big Data are automatically become EOSC services, thanks to having this D4Science infrastructure. So OpenAIRE is also part of our provider, AGI, Zenodo. And we have some synergies with other research infrastructure, which are naturally close to us, like Odyssey from social science, and Ariadne, which is a data infrastructure for archaeological community. And then some services, pervasive computing with slices, and Ariadne as well. So far, the kinds of, so the user community, those which are accessing our data, so we have around almost 10,000 users registered users, a huge production scientific community from our various scientific community, and then we have several methods. We have more than 100 methods which are part of our catalogs, and around 100 unique big data sets. So we are incentivizing the data scientists, so the researchers, to annotate the data, to curate the data, and also to publish as a data papers. So this is another important incentive. So giving to young early stage researchers also an opportunity to have some rewarding from their effort, which is strong, but because they want to curate the data and make it reusable, it needs to be very well done. So this is essentially the path that we have done so far, and we are enthusiastic of. Yesterday we had our last, the second general meeting after 2 years. We had the first one in February 2020, and so after 2 years we couldn't see each other and meet after 2 years. People are very enthusiastic continuing also with ESFRI. So that's it.
The next speaker, I would like to welcome our next speaker, Pavel Svoboda from eBrains. He's Director General of Human Brain Project.
Thank you very much, Jana. Can you hear me, first of all?
Yes, very well. Thank you.
Yes, that's perfect. Thank you so much for having us. So eBrains is the brain research infrastructure. So if you don't mind, I will take you right into the hippocampus, or rather the reconstruction of the human hippocampus that was prepared by our eBrains node lead in Germany, the Jülich Center, on the basis of 530 sections using a technique called polarized light imaging. So as we are touring the hippocampus, I want to make the essential points with regard to brain research and big data, namely that in order to really understand the brain, you need to reach out for greater and greater resolution. So most of the brain atlases today use the millimeter resolution, which allows you to understand the relationship between structure and function, but does not allow you to fully understand the multi-scale brain organization. So for that, you need to go deeper into the level of 1 to 20 micrometers, which is what we are currently pursuing, in order for the researchers to be able to see the smaller details, the fiber bundles, the cortical layers, microcircuits, or cells, because this is what would allow scientists to understand the multi-scale organization of the brain. So back from the hippocampus, this is also an illustration of the type of challenge we're dealing with in decoding the organization of the brain, because we need to look at the spatial, topological, and temporal dimension. So only a few years ago, neuroscientists were studying single neurons. Today, technology allows them to study entire populations of neurons in different regions of the brain over the duration of long behaviors. So this is a revolutionary change in how neuroscience is done. But there is also a temporal dimension here, because we want to study how brains evolve and how they develop during life course and how they degenerate as well. So a few figures. We've heard a lot about the cosmos today in the universe. So we are pretty much in a similar territory here with the brain, 86 billion neurons, each with about 10,000 synapses. So for comparison, the galaxy has about 100 billion stars. We also have 2 to 3 million kilometers of fibers. So this is, again, in fact, more than the diameter of the sun, with 1.4 million kilometers. Not that we are sort of competing directly here, but just to give you an illustration of the numbers we are talking about. And surely this poses a massive challenge in terms of compute and storage. So the type of work that I was talking at the beginning, going towards 1 micron resolution, would require petabytes of data. If you wanted to understand the human connectome, human brain connectome, at the level of the whole brain, this easily takes us into the exabyte territory. And similarly large challenge is posed with large cohort studies in neuroimaging. So big data is our daily bread and butter. And if you would like to read more about it, I would recommend an excellent paper in Science last year by my colleagues Katrin Amons and Thomas Lippert, which was devoted entirely to this theme of brain research and supercomputing. A word about eBrains, where we come from. Well, we are perhaps a little bit unusual among the research infrastructures in Europe, in the sense that we are emerging out of a flagship project, the Human Brain Project, which ends in September of next year, while most of research infrastructures would have emerged from the national facilities. We have a different origin, and the HBP has had a twin objective. It has had a scientific agenda, and building the research infrastructure for the study of the brain has been from the beginning one of its objectives, and it's meant to be a legacy that the project leaves behind it. So we have 5 main categories of services. We start with data and knowledge. We go through the atlases that I have spoken about already. The simulation engines are extremely important in the brain, just like in the study of climate, because there are so many complexities and so many unknowns to explore. Brain-inspired technologies, this is largely neuromorphic computing and neurorobotics, which allows researchers to perform experiments in virtual environments. And finally, the medical data analytics. So what's the value added of eBrains when we look at the data dimension, where we would claim that we have an advantage in terms of fairness and quality of data. And this is because of the emphasis that we place on both of these aspects. So eBrains offers, when you look at brain research, a unique degree of data fundability. We use open-minded metadata schemas, which are better interpretable There is curation by expert neuroscientists, so the data that is on eBrains is always of high quality. And then we link to the different services, which is the essence of what eBrains provides. Now, this idea of emerging from a flagship project is really about co-design, namely that the scientists, the brain researchers, and computer and software engineers have been working literally side by side in developing the tools and services. We also have an extensive high-level support team that guides researchers through the infrastructure, and we have, of course, very regular updates. So data in itself is, of course, important, but what is really essential is to unlock its value. So we definitely spend a lot of time on standards and standardization, given the different inputs that we receive. But above everything else, I think the attention is now focused on supporting researchers in the journey through the creation of workflows and through developing solutions with them, with the use of high-end analytics, so that the research infrastructure really addresses the problem in question. And this is how this would be exemplified. So from the data services on the left-hand side through the curation onto the more sophisticated services that have to do with simulation at different levels of brain organization. And what we are now aiming at is for these different simulators to genuinely talk to each other. This will be a long journey, but nevertheless, we are, I think, making good inroads in ensuring that simulation at the level of a single neuron and simulation at the level of regions of the brain and the whole brain can interact with each other. Of course, this wouldn't be possible without the support of high-performance computing. We also see increasingly the application value of these tools in the clinic by being able to support, in particular, neurosurgery by delineating more precisely the exact place of intervention, courtesy of our modeling and simulation tools. So we have asked ourselves this question, which is in the title of today's workshop, namely how big data needs to be. And in neurodegeneration, it really has to be big data, because mathematical models to predict functional loss from degeneracy simply needs to be derived from massive amounts of data. And this demands also operationalization in scalable computational workflows. So this is in fact, a showcase which we have available on the website, and we'll be happy to describe you in more detail if you're interested. We are also pursuing a project on digital twin technology. So making a digital twin of the human brain, of course, is a very ambitious task, but the journey is started, and the aim would be to have as close as possible representation in the virtual space of the real life object in order to assist, again, the therapeutic and diagnostic processes. Simulation will be with us for some time. I put a quote here from Mark Humphreys, author of the book, The Spike. So the spike is a journey through the brain in, he says, 2.1 seconds. So that's more or less the time that it takes you as you listen to the workshop to think about grabbing a cup of coffee that is sitting next to you. So that's what the book is about those 2.1 seconds. And what Humphreys says is that almost everything we will know in 100 years' time will be from simulation. So yes, there will be increasingly principles of brain organization, algorithms for learning. Certainly knowledge is growing there, but in order to put all that together, simulation will be essential, and simulation will require big data, huge compute and storage capacities. I would want to end with a couple of words on sensitive data, because brain data is sensitive data, and we are also making inroads in that territory by equipping eBrains with a sensitive data service called the Health Data Cloud, which will enable through a network of interoperable nodes for people, for research teams to manage their data, but for that data to be discoverable and shareable on the eBrains portal. And the last word goes to the European Health Data Space, which for us is a big promise. I remember Commissioner Kyriakides saying that this will revolutionize accessibility to health data. And indeed, that's what our research teams very much hope for. And we ourselves are involved in a submission for a pilot project to prepare the grounds for the infrastructural support that will be needed to make this goal of greater accessibility to health data a real one. Thank you so much, Anna.
Thank you very much. Now we go to the last speaker, who is Andrea Passarella from CNR in Italy, who is coordinator of the Italian node in Italy. Italian node, yes, national node in Italy. So Andrea, the floor is yours. I would just like, since we are running short of time, I would like to ask the audience to post questions in Q&A and possibly also the speakers to address them in Q&A. You will see it at the bottom line. Thank you.
Thank you very much, Anna. Let me go in presentation mode. Do you see the slides?
Yes, perfectly. Thank you.
Okay, thank you very much. So thanks for having also us here as LICES. So basically, LICES is a new research infrastructure in the ESFRI framework. It's about supporting computing and communication experimental studies. As it was the case for SKA, we are also building our infrastructure and we will be fully operational starting from the beginning of 2029 with some services available, expected to be available also before, based on what we have at the national nodes already now. So basically, as many of the colleagues before me have said already, we also recognize that digital infrastructures are really one of the fundamental elements of evolution in many scientific disciplines. Why is LICES different? Where it is different is because we think that computer science is a scientific discipline itself that needs a dedicated set of experimental services in order to develop its own innovations in the short, medium, and long term. So LICES is not an e-infrastructure in order to support other disciplines, is a research infrastructure targeting the computer science community and particularly the ICT community to support in doing experimentally driven research at large scales with repeatable and trusted instruments and tools. So we started back in 2017. The design of the infrastructure, and as I said, the main target of our efforts are to help developing and deploy the next generation of computing and networking research results by providing a dedicated set of specialized instruments that allow large-scale European level experimentation across many sites and across an heterogeneous set of instruments that we will integrate together. And in terms of scientific domains, we primarily target networking at many levels, from radio technologies up to all the levels in the protocol stacks, but we also take into consideration computing and data management, and I will talk more about that in a minute. We are not alone in the world. I mean, actually, if I may say, Europe is a little bit lagging behind in this vision, because our colleagues in the US, in China, in Japan, in Asia in general, there are many initiatives that match the objectives and vision of LICES. we are teaming up with them, so the idea is to be the European side of this global effort in building large-scale experimental infrastructure for the computer science communities. This is the current status of the partnership when we enter the ESFRI roadmap. So we are 25 partners from 15 countries. In many of those countries, we have political support. We are part of the national roadmaps, and the counters are going up as we speak. This is the set of partners and different stakeholders that we engaged. Of course, I will not give a detailed presentation. What I would like to mention is that our primary emphasis is on scientific development. So university, research, and academia are the primary, let's say, stakeholders in our view. But because of that, we don't forget industry, also because the sector we are targeting is very, very tightly linked with industry. And fortunately enough, we have support and collaboration with many of the top players in the sector in Europe. And very, very important, we are also partnering with the national research networks and RAN. In many of the countries where we are present, we have strategic collaborations with them, which is very, very important because we want essentially to build a distributed infrastructure where different sites are connected with each other through high-speed links. Because we are starting, okay, sorry for the animation, I will not go into that. Just to mention that one of the initial steps is identifying the research priorities that we want to support in our discipline, and in order to do that, we have an established methodology that is already up and running, and which allowed us to identify the main research priorities that we want to support in the different fields that we target, including wireless networking, data-driven infrastructures, operational management, and the different verticals. And when it comes to data, which is the main topic of today, we think that there is a perfect match and a lot of synergies between networks and data considered as research disciplines in themselves. Essentially, networks and the evolution of networks needs big data because networks are not anymore dumb pipes to transmit bits, but they are more and more complex systems where you need to do a lot of automation. And in order to do automation and self-configuration, you need data in order to understand what the network is doing, and artificial intelligence on top in order to automatically configure your network. So the network is basically built on big data analysis. But on the other hand, big data is built on networks because more and more data analytics is decentralized. You can't just put all your data in a single data center and do the analysis. So you need to configure the networks in such a way that your data analytics are actually the most efficient that you can. And this is a vision that we share with one of the previous RIs that have been presented, particularly So Big Data, and there is a strategic partnership between Slices and So Big Data with Instantiate, for example, in many joint initiatives that we are carrying on at the national level in Italy. With respect to the data management that we consider in Slices, basically we support data at all those stages of the experimental life cycle. The most important point, I would say, that in the interest of time, is that we are really committed in order to support data-driven experiments also in the networking area, and to make results of the experiment widely available in a trusted way in order to increase the repeatability and the trustworthiness of experiments, which is something that unfortunately in our community is not so common as in others. And in order to do so, of course, we have our own data-driven services for the infrastructure, but we heavily rely on EOS services. And with respect to that, basically Slices is on the one hand a data provider for that EOSC services for everything that deals with data management, data processing, data curation, and so on and so forth. And on the other hand, we are going to link with EOSC in order to be visible as also a service provider in their catalog. So that's it from my side. Thanks a lot for your attention. Any questions, I would be very, very happy to take them.
Thank you very much. Unfortunately, we have already exceeded the available time, and we have another audience waiting for us in another session. So unfortunately, there were no questions in Q&A posted and nothing in the chat. But personally, I would like to thank you very much, all of you, for the presentations of today, which certainly enlightened my view on the activities that you have, and particularly highlighted the big issues that we have with the big data when it comes to research infrastructures, and something that certainly needs to be looked at with a lot of interest. I would like to thank you very much, and see you next time at another occasion.
Thank you very much. Bye-bye.
Thank you.
Thanks, everyone.
Thank
Bye.
you.